Today we will discuss some aspects of gamma ray decay. An excited nucleus can emit gamma rays and come down to a lower energy state, let us say the ground state for example. So, let us first look at the kinematics as usual. So, one is the energy conservation. So, let us consider E x star as the energy of the initial state and E x as the energy of the final nucleus, energy state of the final nucleus, and you have the energy of the photon gamma particle gamma ray emitted, and when the photon is emitted, you will also have the recoil kinetic energy for the resultant product nucleus. Let us denote that by T recoil Tr, the kinetic energy corresponding to that. This is one thing, and therefore, the energy conservation equation is initial energy E x star is equal to the sum of the final state energies E x plus E gamma, which is the energy of the photon emitted, plus the kinetic energy of the recoiled nucleus or the atom. Now, momentum conservation will tell us that the 3 momentum of the initial nucleus P x star should be equal to the 2 particles, the sum of the energy momenta of the 2 particles in the final state P x and P of photon. Let us consider as usual the rest frame of the final the rest frame of the initial nucleus. In that case, we have P x star equal to 0, which will lead to P x equal to minus P gamma. Okay. And magnitude of the photon's momentum is equal to the energy of the photon divided by the speed c. Because it is a massless particle, the only energy is the kinetic energy, and therefore, momentum related to this motion is energy divided by c, which is in magnitude also equal to P x, momentum energy, the magnitude of the momentum of the daughter nucleus. Kinetic energy T r is, we will use the non-relativistic expression, which is enough here, P x square divided by twice mass of the daughter nucleus. This is equal to E gamma square over c square, which is P x square in magnitude, into 1 over 2 m x. Okay. So, if we consider the define what is called the excitation energy, the energy difference between the lower energy state of x and the excited energy state, the initial energy state of the nucleus x star, then let us denote it by delta E, that is equal to E x star minus E x, correct. And energy conservation will tell you that this is nothing but energy of the photon plus the kinetic energy of the recoil energy of the daughter nucleus. This, because T r is now written in terms of E gamma square over twice m x c square, we can write delta E as E gamma plus E gamma square over twice m x c square. So, delta E, the difference in the excited state energy and the lower state into which the nuclear state is decays, is not entirely available to the photon which is emitted, because X can have a small recoil. It should have a small recoil, however small it is, because of the momentum conservation. So, the total energy available for the electron is slightly less than the excitation energy. Okay. In fact, we can try to write get E gamma in terms of delta E and mx by considering this quadratic relation. Okay. So, let me write the quadratic relation in a slightly different way. E gamma square plus, let me multiply the expression here by twice mx c square, and that will give me E gamma square plus E gamma into twice mx c square minus delta E into twice mx c square is equal to 0. So, this will give me, I can use this quadratic equation in E gamma to get E gamma as minus twice mx c square plus or minus under root 4 mx square c 4, the coefficient of E gamma square of that, minus 4 times coefficient of E gamma square, which is 1. So, that is 4 times the coefficient of the constant term. The constant term has a minus sign already there. So, this becomes plus 4 into 2 mx c square times delta E, everything under root, which I can write as minus 2 mx c square plus or minus under root. Okay, I will take 2 mx c square out, and then it is 1 plus 2 delta E divided by mx c square in this thing. So, essentially it is, if I take mx c square or twice, there is already an overall factor of 1 over 2. Okay. So, therefore, this becomes mx c square minus 1. If I take the negative root here, okay, negative sign in the second term, then the total is a negative term, because the first term is negative. Therefore, that is not a valid physical expression for the energy. Total energy of the photon should be positive. So, the only possible value is plus here, and we have an under root 1 plus 2 delta E over mx c square. Expanding this under root, I will get mx c square minus 1 plus 1 plus twice delta E over mx c square 1 over 2 of that, minus, sorry, this should be plus here, and then there is a minus 1 over 2 square delta E over mx twice finally, this will turn out to be E gamma is equal to mx c square into delta E over mx c square minus delta E by mx c square all square 1 over 2, and that is equal to delta E minus delta E square divided by mx twice mx c square. Okay. So, as I said earlier, the energy of the photon is slightly smaller than the energy of the excitation energy delta E. Okay. Take an example of oxygen isotope O17. First excited state of this, let me denote it by delta E1, is equal to the energy corresponding to the first excited state is 4.549 MeV. That is the excitation energy of first excitation energy of O17, and mx is 16.999131 atomic units, which corresponds to 15834.724 MeV per c square. Okay. Or okay, if I take mc square, this turns out to be MeV, so much of MeV. So, I think there is no factor of 2 here maybe. Okay. So, if I consider the correction from delta E square over 2 mx c square, it is approximately 0.7 into 10 power minus 3 MeV, about 700 electron volts. So, we can actually neglect this compared to 4 or 4.5 MeV, which is this one is something like 4 orders of magnitude smaller than that. So, for all practical purposes, we can actually take E gamma to be order of this equal to delta E, the excitation energy. But if you are considering a solid and gamma emission from the nuclei of the molecules or the atoms of the solid, then a few hundred of electron volt is enough to actually eject the nucleus from that. So, the recoil, sometimes the recoil is high, or even the kinetic energy associated with the recoil is about a few hundreds of electron volts. That is enough to actually make the nucleus come out of the solid. This is called radiation damage, okay, of the solid, obviously. So, basically for recoil kinetic energy of 100 GeV or of few hundred GeVs, atoms in the solid may be ejected . But for low energy photon rays, so small excitation energies, this may not happen, but for high energy gamma rays, this is a possibility. So, that is a side remark that we have. All right. Now, let us consider the probability of the decay of the thing, probabilities gamma decay. We will not go into again the details of the quantum mechanics, exactly similar to the beta and alpha decays. We will here also restrict to some a bit of a qualitative understanding of the gamma ray, etc. In fact, in this particular case of gamma decay, we will only discuss, just mention some properties of the gamma decay without really going into any calculations of this as far as the probability etc. is concerned. But one can actually do a full quantum mechanical calculation based on whatever model that you have and electromagnetic model that you have, of course, and then you can try to compute all these probabilities for various different gamma emissions. Here we will restrict ourselves to just simply stating some of the or giving some information about this. So, first let us look at what different types of gamma rays are possible, whether we can classify this in some fashion. Okay. Photon emission is basically due to multiple oscillations, right, purely looking at from the point of view of electrodynamics. Quantum mechanically also this can be treated in a similar fashion. So, we can actually think about the gamma decay or the photons which are coming out of the gamma decay through the gamma decay as either due to electric multipole transition or as magnetic multipole transitions. So, that is one of the type of classification that we can have. The transitions could be either electric multipole transitions or magnetic multipole transitions. If you ask what is the probability for electric dipole multipole transitions and magnetic dipole multipole transition, multipole meaning either dipole, quadrupole or higher poles. Okay. Probability, how does it go as you consider different multipoles? It looks like it is basically probability is reduced for higher multipoles, higher order multipoles compared to the lower multipoles, which means multipole order 1, which is actually the dipole transition, is more probable if otherwise possible compared to the quadrupole, which is the order 2 multipole transition. So, if both of these are possible, then the first order, which is the dipole transition, will be dominating compared to the quadrupole or the order 2 transition. That is one thing. Another thing is comparing the magnetic and the electric. When we compare the magnetic and electric of the same order, say same multipole order, magnetic transition is less likely compared to the electric transition. All right. So, if it is the dipole transition that we are talking about, magnetic dipole transition is less likely compared to the electric dipole transitions. In fact, there is one more aspect to it, which is the parity consideration that we will come to in a moment. For that, we actually need to also think about, understand the angular momentum. So, let us look at the angular momentum associated with gamma rays decay. There is the spin of initial excited state, which is the initial state. Then there is the spin of the final state, which is the de-excited state. So, spin of de-excited nucleus, that is the final or daughter nucleus, and with the multiple emission of the photons, there is the photon which carries some angular momentum. In fact, the multiple order is basically the different multiple orders will have different angular momentum associated to the associated photons. So, this is the angular momentum corresponding of the angular momentum of gamma ray or the photon emitted corresponding to the order of multipole transition. For example, L equal to 1 corresponds to dipole transition, as I already said, and L equal to 2 corresponds to quadrupole transition. All right. Now, the angular momentum conservation will tell you that you have I is equal to I f plus L, plus is an angular momentum addition. So, let us take an example. Hafnium 177 has a ground state with spin 7/2 and parity negative ground state. It has the first excited state in 9/2 minus and it has another excited state, in fact, the third excited state in 9/2 plus. So, it will look like something like this. So, this is 7/2 minus and here you have 9/2 minus and 9/2. Say 9/2 plus, and there is in between something which is actually 11/2 minus. So, now let us look at the transition from 9/2 minus first excited state, okay, of hafnium 77 to the ground state of hafnium 177, which has an excited state, which has an angular momentum or the spin state of 7/2 and parity minus. Here the possibilities are, so 9/2 minus to 7/2 minus, I initial is equal to 9/2, I final is equal to 7/2. So, possible L values are 9/2 minus 7/2, the magnitude of that, etc., up to 9/2 plus 7/2. So, this is 1, 2, 3, etc., up to 9/2 plus 7/2 is 8. Okay. So, as we said, higher order poles are less probable compared to lower order. So, maximum possibility is for 1 compared to 2, 3, 4, etc. And if 1 is possible, then it will happen. What type, electric or magnetic? That will also depend on change in parity. Now, in this case, no change in parity, right? And for magnetic transitions, change in parity, let me denote it by delta pi for magnetic transitions of type order L. See, if it is magnetic dipole, then L equal to 1, etc. This is equal to minus 1 power L plus 1. This is what I am stating without actually showing any proof for this. Okay. We will not give any arguments even to suggest how to get this. I will leave it to you to go look at this in your textbook or any other book that deals with gamma rays. And for electric transitions, delta pi, let me denote it by EL, electric transition of order L, it is minus 1 power L. So, between magnetic and electric of the same order L, if one has change in parity, the other will not have change in parity. So, here just purely looking at the L values, possible L values, possible transitions are electric dipole, let me denote it by E1, electric quadrupole, etc. The higher poles let us do not worry about, because they are less likely, and it is possible that M magnetic dipole, magnetic quadrupole, etc. With parity consideration, E1 is associated with a change in parity, E2 is associated with no change in parity, because L is equal to 2 and delta pi for electric transition is minus 1 power L. If L equal to 2, it is plus 1. So, E1 is ruled out in the case of, in the present example, 9 by 2 minus going to 7 by 2 minus, because there is no change in parity, whereas E1 should have a change in parity. So, E1 is not possible. E2 is possible. How about the magnetic transitions? In the case of magnetic transitions, M1 is associated with no change in parity, L equal to 1 case. So, L plus 1 is 2. So, minus 1 power L plus 1 is minus 1 power 2 is positive, whereas M2 is associated with change in parity. So, that is not possible. So, we can say that it is of type E2, but it is also possible that it is M1. Well, we already said that the higher poles are less likely compared to the lower poles, that is, there is a magnetic dipole transition possibility and a electric quadrupole transition possibility. And then we also said that the properties of gamma decays, if we analyze, it tells us that magnetic transitions are less probable compared to the electric transition. Since the magnetic transition allowed here is 1 order smaller compared to the electric transitions, we can expect that this particular case, the transition will have both magnetic type and electric dipole quadrupole type. So, it will be a kind of a mixture of magnetic dipole and electric quadrupole type. Now, let us consider the transition from 9 by 2 plus excited state to the 7 by 2 minus ground state. Here again, possible L values are 1, 2, 3 etc. up to 8, and but the possibilities therefore maybe are E1, E2, M1, M2. Let us stop at this, and higher order multiples, but they are less likely, okay, like in the earlier case. Now, change in parity delta pi is yes. So, the initial parity is positive, final parity is negative for the nucleus. Therefore, the gamma ray should be associated with the multipole which has with change in parity. As we said earlier, E1 is associated with parity, change in parity, and therefore, that is possible, but E2 is not possible because E2 corresponds to no change in parity. Similarly, for the case of magnetic transition, M1 is not possible, but M2 is possible. And now, if you compare E1 and M2, as we said, electric type of transition is more likely compared to magnetic type, and again higher order pole is less likely, that is the quadrupole transition is less likely compared to the dipole transition. So, M2 has double disadvantage here compared to the E1. Therefore, we will say that predominantly it is an electric dipole transition. All right. So, that is one of the things that we can understand by just looking at the spin and parity of this one, and in fact, we can do a more involved analysis by looking at the probabilities and then from our theoretical calculations of the dipole transition and see whether that agrees with the observations, etc. But we will not go into such details in these lectures. We have another possibility in this case, in the case of excited states decaying into ground state or any other low energy state. It is possible that instead of emitting a photon, the excitation energy of the nucleus is transferred to the atomic electrons, thereby emitting an electron which is basically an atomic electron. So, this is unlike the beta decay. In the case of beta decay, a neutron was converted into a proton and an electron was created there, which was not present earlier. But in the case of in this case, an atomic electron which is already existing in the atom revolving around the nucleus gets the energy from the excited nucleus. The excited nucleus will transfer the energy to the electron, atomic electron, and such atomic electrons are emitted. So, E minus is an atomic electron, and the atom becomes a positive ion. So, let me just denote it by plus x plus, just to remind you that it is an atomic electron which is going away from that. This process is called internal conversion. Okay. So, if I look at the kinetic energy of electron, emitted electron, let me denote it by T, that is equal to the excitation energy minus the binding energy. To release an electron, you have to give some energy to the atom, which is equivalent to the binding energy of the electron. So, B is the atomic binding energy, not the nuclear binding energy that we were talking about in the case of a nucleus, but the electron's atomic binding energy. Of the electron. It actually depends on from the which shell the electron is emitted, from the K shell, from the L shell, or whichever shell. Okay. The binding energy will depend on that. All right. So, from here we actually can make another statement. Let me denote lambda E as the probability of internal conversion and lambda gamma is the probability of gamma emission from an excited state. The total probability of de-excitation is lambda t equal to lambda gamma plus lambda E. So, this is always there, that one has to, there will be a small probability for such internal conversion, which is always possible. In fact, one can actually define the coefficient of internal conversion or internal conversion coefficient, which is basically giving you the relative strength between the probability for emission, internal conversion, emission of an electron, and probability for gamma ray emission. It is usually denoted by alpha. Sometimes with a subscript, in fact, you can actually have a subscript for denoting the shell in which the electron is emitted, from which the electron is emitted. Now, let us consider, when we consider a higher excited state of the nucleus decaying down to a lower excited state, it is possible that it can either convert to a lower excited state by emission of photons, and it is possible that we are considering the not the first excited state, but second or third excited state of the nucleus. In that case, it can de-excite into either the ground state or to the first excited state, etc., whichever is the lower energy state possible. So, in such cases, when we consider the probability, we will have to add all the probabilities of for this. So, let us say higher excited states may de-excite into one of the lower states, right. So, that is what just now we said. So, let us consider an example of one ground state, first excited state, second excited state, third excited state. And if an atom is in the third excited state or nucleus is in the third excited state, it can emit a photon and come down to ground state. That is one possibility. Let us denote that as process A. Another possibility is that it can go down to first excited state by emitting photon again B, and third possibility is to go to 2 by emitting a photon process 3. Probabilities for these to happen will depend on various things, like whether it is an electric transition or a magnetic transition, what kind of dipole, whether it is a dipole transition or quadrupole transition or higher pole transitions, etc. In turn, that depends on the spin and parity states of the ground state, first excited state, second excited state and the third excited state, and also depends on the atomic weight, the excitation energy itself, and the energy gaps between the first and third excited state, second and third excited state, etc. We did not explicitly write down any of these expressions or the dependence of these quantities on the probability, but the probability does depend on all those things. Okay. So, we will not go into those details, but let me denote the probability for this process A, that is the excitation de-excitation into ground state as lambda A, the one to de-excitation to first state as lambda B, the probability for de-excitation into second excited state as lambda C. And then there is also a probability for internal conversion. In fact, the probability for internal conversion is also many, that it is probability for internal conversion by emitting a K shell electron, emitting an L shell electron, different electrons in that this thing, close by electrons, but it could be L shell, K shell or whichever other shells. So, when we talk about a probability for internal conversion, let us say we add all of those probabilities for emission of K shell electron, N shell, L shell electron, etc., call it total as lambda E. So, this is the internal conversion probability. Then the total probability lambda T, let me denote it by lambda T, is lambda A plus lambda B plus lambda C plus lambda E. Okay. Even in the case of lambda A, it could be electric and magnetic together, like we saw in the example of hafnium. So, now the half life, for example, of decay or de-excitation. Okay. So, half life T half of third excitation, excited state, is simply log 2 over lambda total. So, we have to actually compute the partial widths or partial probabilities into decay to different channels, okay, and then add all the probabilities, and then the total probability will get, and the half life will depend on the total probability. So, 1 over that. Okay, so we will stop here for the time being, and then come to other discussion in the next class.